So welcome to tonight's SLAC public lecture. My name is Lance Dixon, and I'm filling in for the Communications Director, Neil Calder. And tonight we've got a great topic and a great speaker lined up for you. Our speaker tonight is Dr. Risa Wechsler, who's a faculty member here at SLAC and Stanford University, and she's a member of the Kavli Institute for Particle Astrophysics and Cosmology. And as a cosmologist, she's interested in some of the broadest scope questions you can imagine, starting from tiny fluctuations in the early universe and ending up in the largest structures we can see. She got her SB from MIT in 1996 and her PhD from University of California, Santa Cruz in 2001. She then did a postdoctoral fellowship at the University of Michigan and at the University of Chicago, where she also held the prestigious Hubble and Enrico Fermi fellowships. And we were fortunate to attract her here to Stanford in 2006. Now, besides her research and teaching, some of you may also know her as a blogger on the blog cosmicvariance.com. And her research on galaxy and cluster formation also sheds a lot of light, so to speak, on the nature of the mysterious substances of dark matter and dark energy that pervade the universe. And so tonight she's going to tell us all about the deep mystery of dark energy.
Thanks, Lance, for that introduction, and thanks to all of you for being here. So the focus of my talk today is dark energy, and you may or may not have any idea what those words mean. Cosmologists in the 21st century throw around a lot of funny words and concepts, but that is actually because the universe is a pretty funny place. And to my mind, dark energy is really pretty top up there on the list of funny concepts that we have in the universe, and that's the reason for the subtitle of my talk. But like it or not, it's a concept that we're really going to have to grapple with because it seems to be what most of our universe is made of. And that's really the focus of my talk today, is what is the universe made of? Okay? So that's the question that I'm going to spend most of the time today talking about. And it's really a pretty amazing situation that we find ourselves in. Just in the last decade, cosmologists, physicists, and astronomers working together have basically, we think, figured out what the universe is made of. We think we know the answer to this question. Okay? So that's a pretty amazing thing. This is a question people have probably wondered since people wondered about much of anything besides how to eat. And we think we've answered it, except for the fact that it's a really, really strange answer that we don't understand at all. Okay? So that's what I want to try to explain to you. And sort of alternative talk title that I just thought of this weekend, this is not your mother's universe. And what I mean by that is really, this is a totally different picture of the universe that we had a generation ago. It's a totally different picture of the universe than we had even 10 or 15 years ago. It's a different picture than we had when I started graduate school. So it's a pretty exciting story. And this question of what is the universe made of is deeply connected to a lot of other questions that you might find interesting. How old is the universe? How is it developed from its earliest stages to the things that we see in the sky today? And what is its ultimate fate? And it turns out not only are these things all related to that first question about what the universe is made of, but they're also related to this concept of dark energy, and that's why I'm talking about that here today. So let me just take a step back from dark energy and give you sort of what the universe was made of about 450 years BC. So this was the Greek concept of the universe. This concept is apparently actually pre-Socratic. So earth, water, wind, and fire. That was what the universe was supposed to be made of. Okay? So we progressed a little bit. In 1969, we lost an element. It got a little bit simpler. Okay, no, actually, let's back up. Let's go back a century. this is what we thought the universe was made of in 1869, when Mendeleev wrote down the periodic table. So it wasn't actually quite this complicated in 1869. We filled in lots of pieces since then, but the start of it happened at that time. And this is actually most of the universe that you and I interact with in our daily lives. This is the things that we're familiar with here on Earth. Okay? And this is what astronomers call baryonic matter. Everything in this table is what astronomers call baryonic matter, or sometimes, now that there's all this strange stuff, they call it normal matter. Okay? And all that really means is stuff made of atoms. Okay? Stuff made of protons and neutrons and electrons, the normal stuff that we interact with here on Earth in our daily lives. Of course, the picture here, this periodic table picture, is actually a little bit more complicated, or depending on whether you're a particle physicist or not, a little bit simpler. So this is the picture of the universe that's been developed by particle physicists, many of them here at SLAC, really doing fundamental work on what makes up atoms. And this is the sort of straightforward picture that they came up with, except for it's really a little bit more complicated than that. There's lots of interactions. But the basic picture is there's some quarks, which are the things that make up protons and neutrons, some other particles called leptons. An electron is an example of that. And then there's some force carriers that mediate the interactions. The photon is probably the one you're most familiar with. That's the thing that carries light. Okay, so this is this really beautiful picture, the standard model developed originally in the 1970s. We haven't really broken it yet here in accelerators in any way, except for it turns out that when we go to the whole scale of the universe, astronomers have now figured out a very different picture. Okay? And in this picture, only 4% of the universe is made up of all of the stuff that I just told you about. Okay? Only 95% of what the universe is made of is not on the periodic table, nor is it in the standard model of particle physics. So this is a very puzzling state of affairs. Stars, which are the main thing that we think of when we think of what is out there in the universe, only are half of a percent of what the universe is made of. The chemical elements that make up you and me, everything in the universe that's heavier than hydrogen and helium, is actually only a tenth of that. And all of this stuff is just about 4%. Okay? The rest of the mass in the universe is something called dark matter. And that's, we think, some kind of particle that doesn't emit light or interact with light at all. And if you were here 2 months ago, Marusha Bradic gave a really nice talk about dark matter. I'm going to mention dark matter in my talk because it's sort of essential for telling the whole story. But the rest of the piece of this pie is this funny stuff called dark energy. Okay? That's what I'm going to try to focus on. But in order to talk about this, I really have to talk about sort of what is our basic picture of the universe, what is the rest of it, and some basic facts of the universe. So I'll start there. So the first thing that you notice if you have a telescope that's big enough is that the universe is filled with galaxies. And it actually is it's less than 100 years that we've understood that fact. Hubble was the first person to realize that there were galaxies outside of the Milky Way, which were separate entities. Okay? Before that, they called these things nebulae. They thought they were fuzzy blobs on the sky. They weren't really sure what they were, but they thought they were part of our Milky Way. So Hubble's breakthrough came from a really fundamental method in astronomy. It came from a fancy way of figuring out how to measure distances in the universe. Okay, so that's how he actually first realized that the universe was filled with galaxies. And it's also how he first realized that the universe is expanding. Okay, and the basic thing that Hubble was able to do, he was able to identify a kind of object. This was a particular kind of star called a Cepheid variable star, which astronomers call a standard candle. And the basic idea behind a standard candle, it's just like a light bulb. You know how much luminosity it emits. And so if you put it far away and it got dimmer, you would know how far it was to that source. Okay? So that's what Hubble did. Basically, he knew the absolute brightness of these stars. And once he knew their absolute brightness, looking at how their apparent brightness told him how far away they were. Okay? So the other thing Hubble did was then measure how fast these galaxies were traveling. And the thing that he realized was that these galaxies were traveling away from us. They had velocities that were not actually constant, but the farther away they were from us, the more rapidly away from us they were traveling. Okay? And so this is the famous Hubble's law, which just says that the velocity of an object is proportional to its distance away from us. Okay? And the way that he measured these velocities was by looking at something called the spectrum. Right? If you've heard of a redshift, that's just basically it's measuring the spectrum of light from a galaxy. And you can see these are 5 different galaxies that are at different redshifts, meaning different distances away from us. And you can see that the whole spectrum is shifted into the red. This is the wavelength of light here. So the whole red spectrum is shifted into the red when something's traveling away from us. So that's a mechanism of measuring velocities. And so this was Hubble's original plot from his paper. It turns out he actually got the number wrong, the so-called Hubble constant. He got the number wrong by an order of magnitude, but but the basic trend has held with amazing precision to the present day. Okay, so given this picture that the velocity is proportional to the distance, that implies an expanding universe, right? So the basic idea here is if this is you, things are traveling away from you here. They're traveling more rapidly away from you the farther they are. You can extrapolate that expansion backwards, okay? You can basically just imagine these things were all a little bit closer to you, okay? And you can extrapolate the entire expansion backwards. And that's the basic idea of the Big Bang, okay? The basic idea of the Big Bang is just this idea of the expanding universe. And that idea has a lot of implications, okay? So the thing we really know about the Big Bang is that we know the universe is expanding. And that implies that in the past it was much, much denser than it is today. Expansion also dilutes the particles, right? So that's essentially what it means to be denser. So today, particles are very spread out. In the past, they were much, much closer. And and when things are denser, they're also quite a bit hotter. And most of our evidence for the Big Bang essentially comes from looking at various aspects of this process of cooling and diluting. Okay? So here we are today in a sort of cold, empty universe. If you extrapolate that back in time, the universe got hotter and hotter and hotter. And I'm not going to have time to go through this detailed picture, although it's really a pretty exciting one. But there's lots of evidence for the Big Bang, which comes from, for example, what happened in the first 3 minutes was that the universe got cool enough so that hydrogen and helium could form. And that process, the rate at which that process forms tells us quite a bit about this Big Bang process and this expansion. So that's just one piece of evidence, and we'll talk about a couple others in the rest of the talk. So if the universe is expanding, if it's expanding at a given rate, one thing you can ask is, what will stuff in the universe do to that expansion rate? Okay. Well, what stuff does is gravity basically pulls things together. Okay, and that process happens not only on Earth, but it happens in the entire universe. Gravity essentially acts on everything in the entire universe. Whoop, whoop. So gravity will slow the expansion rate down. And the more stuff you have in the universe, the more matter you have in the universe, the faster it will slow down. Okay? So this plot just shows the separation between galaxies, or the scale, in some sense, of the universe as a function of time. And if we're here now, you can sort of ask, okay, if I can measure the expansion rate today and extrapolate it into the past, if the universe is empty, it implies this kind of age. If the universe has stuff in it, that implies that the expansion rate has to change. Okay? And so it'll expand more and more rapidly. And so in essence, this expansion rate is like a scale. It's a way of measuring how much stuff there is in the universe. Okay? So I'm not used to this thing, sorry. So the more stuff you have, the more rapidly your expansion slows down. And there's a magic number that cosmologists talk about quite a lot called the critical density. Okay, so that's a particular amount of matter that has just enough matter for it never to recollapse, but to always slow down a little bit more than it is slowing down. And that's just, imagine that you were a baseball player with a very, very, very strong arm, and you threw a baseball and tried to reach the Earth's escape velocity. Okay? If you don't throw it very hard, it'll come right back down immediately. That's just like the universe having a lot of mass. If you throw it very, very hard, it might actually escape. So the expansion rate does all kinds of other things for you. The expansion rate is also like a clock, right? Like we said, if you can measure the age of the universe essentially by extrapolating this plot backwards. Okay? And the age will depend on, again, how much stuff there is in the universe, because this expansion rate will change depending on how much stuff there is in the universe. Okay, so Einstein taught us something else about stuff in the universe. And Einstein taught us that basically everything in the universe causes gravity, and everything is affected by gravity. Okay? And what affected means is lots of different things, but one of the things that affected means is that gravity can actually curve space. And this can happen globally on the whole scale of the universe. And that's what people are talking about when they talk about the curvature of the universe. And it can also happen locally on small scales. And that's what people are talking about when they talk about gravitational lensing. Okay? You might have heard of gravitational lensing. I'm not going to have time to talk about it very much today. Gravitational lensing gives us one of the best pieces of evidence for dark matter, because it actually is able to measure how much stuff there is instead of how much light there is. The basic idea here is that light rays like to travel in straight lines. And so if space is curved, the light rays will bend around them. And the amount of bending tells you about how much mass is there. So one implication of this theory is that the expansion rate of the universe and its curvature and the amount of matter that live in it are all intimately related. Okay? They're all just directly related through this theory. Okay? So we just mentioned briefly geometry. This expansion rate also measures what astronomers call the geometry of the universe. And this is a little bit of a confusing term. Geometry is based on the total amount of stuff, which could be matter or some other kind of stuff. I'll give you an example of that other kind of stuff in a few more minutes. But what geometry says is the thing astronomers call flat means that space is like you learned in your high school geometry class. If you draw two parallel lines, they always stay parallel. And if you draw a triangle, the angles end up adding up to 180 degrees. So that's what we mean by flat. We don't actually mean flat like a pancake. It's hard to think in your mind about what it means to not be flat in 3 dimensions, so people often give two-dimensional examples of this. But one of the key results of general relativity is that this geometry is directly related to this expansion history. Okay, so a universe which recollapses on itself is closed, and a universe that was, like I told you, this critical universe is flat. Okay, so there are other ways to weigh the universe. One of them is by looking at dynamics on lots of different scales. So the amount of stuff that we can see from the shining stars, as I mentioned, is only a very, very tiny fraction of this critical density, of the amount it would take to essentially recollapse the universe. So one thing you can ask is are the stars everything there is? And light doesn't have to always be in the same place as mass. You can see that even in this room. There's lights up there. You know, there's some pretty massive people down here. No. And this plot of the United States shows that as well. There's lots of lots of light here in California. There's lots of mountains here in Colorado which have mass and aren't giving off a lot of light. So maybe the universe is like this as well. And just like we can measure motion on the scale of the whole universe, we can also measure it locally on smaller scales. And the first very interesting measurement of this type was actually done in the 30s by Fritz Zwicky, who was kind of, you can see in this plot, a little bit of a cantankerous guy. So what Zwicky found was he measured the velocities of galaxies in something called the Coma cluster, which is one of the very nearby clusters. And he found that the velocities of those galaxies were so big that there had to be more stuff there. That if the only stuff that was there was the light, those velocities would make the cluster fly apart. Okay? And that was, in essence, the first evidence for dark matter. Again, in the 30s, there was other very convincing evidence for dark matter based on similar measurements, but this time looking at galaxy rotation curves done by Vera Rubin and her collaborators in the early 70s. And I'm not going to have time to talk about dark matter in a whole lot of detail, but I want to just give you this brief summary. Basically, there's tons now of observations that indicate that most of the mass in the universe is dark. And those observations are on just a huge range of scales. They're on small scales even within the solar system. They're on scales of individual galaxies. They're on scales of clusters. You might have heard in the news some recent results on the Bullet cluster, which is now, I think, really overwhelming evidence for dark matter. But there's also evidence on the scale of the whole universe that there has to be more mass that's not in atoms, essentially. Okay? And so we think that's about 85% of the mass in the universe. Okay? And by mass here, what I mean is stuff that's clumpy, and I'll talk about the clumpy universe again in a few minutes, but that's essentially what I mean by mass, stuff that gravity acts on. Okay? That's what you can think of by mass. And the key feature of this dark matter is that it doesn't emit light or radiation. Okay? So it's very different from gas particles. When gas particles are hanging around each other, they bump into each other, they cool down. That doesn't happen with dark matter because they can't radiate, they can't cool. Okay? And that's actually a very key feature for dark matter and for understanding galaxy formation, which I won't have time to talk about today, but that's a lot of what I work on. So although we have not directly detected dark matter, there are lots of plausible explanations. We think that it's probably some particle that we haven't detected yet, and there's actually a reasonable chance that that particle will be detected in the next 10 years, or at least that we'll see some evidence for it outside of just its effects in the universe. So another basic fact about the universe that we can see now very vividly in recent galaxy surveys is that the universe is very clumpy. Okay? So you can see that even on our scale of a planet or the solar system. Although most of space is very empty, we have things like planets and stars, okay, and that wouldn't happen unless it was clumpy. So it's clumpy enough to form objects, but even those objects are themselves very clumped. And this is an image of the galaxy distribution in a galaxy survey called the Sloan Digital Sky Survey, which actually surveyed 8,000 square degrees of the sky, so that's about a fifth of the sky, and measured positions on the sky and redshift, so in essence 3D distances for more than 1 million galaxies, and got actually pictures in 5 different colors of close to 100 million galaxies. So this is just a phenomenal survey that just finished essentially in the last year. And one of the things that you see in this picture, every tiny little dot in this picture is a galaxy. And you can see that they're not just randomly distributed. Okay? They're very clumpy. So how did that clumpiness get there? And was it there in the beginning? How did that appear? Well, we think the best idea we have for the origin of that clumpiness is something called inflation. We actually can see how clumpy the universe was now about 400,000 years after the Big Bang, using something called the cosmic microwave background radiation. And remember when I told you about this process of cooling in the Big Bang? This was a special moment in that process of cooling. And this was the moment in that process of cooling when photons were basically able to escape from the rest of stuff. So light particles from that time have actually been traveling to us from 400,000 years after the Big Bang, and we could actually see how they're distributed in the sky. And it turns out that they're distributed very, very smoothly. What's been done in this picture is that those clumps have been blown up. And each fluctuation you see here is 1 part in 100,000. Okay, if you just looked at the picture, it would be exactly smooth. So the clumps have been blown up several orders of magnitude. But this is what we see. If you blow those clumps up, you see a clumpy universe. And the best idea we have for what originally formed that clumpy universe is that in the very first fraction of a second, this process called inflation basically expanded the universe much, much faster than the speed of light. Okay, so you might have heard that things can't travel faster than the speed of light, but things can't travel through space faster than the speed of light. There's no limit on how fast space itself can expand. Okay? And this is a theory that predicts that space itself expands much, much faster than the speed of light in the very early universe. And what the consequence of that process is that quantum fluctuations, basically particles that can pop in and out of existence due to quantum field theory, get stuck. So by the time they pop into existence, and by the time they try to pop back out, the universe is too big. And so they get stuck. And that's the process that we think seeded these fluctuations. And the amazing thing about having this very detailed picture, this picture was actually just taken in 2003. Now we can take this picture as, in essence, some sort of initial conditions for our universe. Okay? And most of the work that I do sort of starts with this as the beginning, about 400,000 years after the Big Bang, and tries to see what happens next to what happens to these clumps next. And this is just a movie made by some of my collaborators about how that clumping process proceeds. And the time here is in billions of years from now. So we think the universe is about 13.7 billion years old. So this is about 4 billion years after the Big Bang, nine ago. And you can see this clumping process happening. What's in essence happening here is that gravity is taking the places where the universe is a little bit more dense and making them a lot more dense. Okay? And that's the entire process of structure formation. That's how we think we get that picture of the galaxy distribution today, is through this clumping process. So it turns out that the rate of this clumping process provides another very nice way to weigh the universe. And so the basic idea here, right, is just that gravity is the thing that's making those small clumps bigger. Gravity was the thing that was making that movie evolve. And I should have said, actually, in that movie, I sort of took out the expansion of the universe. So during that whole time, the universe should have been expanding, except for then it would be harder to see. So I took that piece out. But this process of gravity acting on those clumps depends on how much total stuff you have. So the more mass you have in the universe, the faster that process happens. And so looking at the structure that we have in the universe today and comparing it to the structure that existed in the universe 400,000 years after the Big Bang is another very, very good way to measure how much stuff is in the universe. And this is just an example from two of those kinds of simulations that I was telling you about. This is a universe with low density, not a lot of stuff. And this is a universe with high density, a lot more stuff. This is a universe that has the so-called critical density. So the state of the universe just about 10 years ago, when I was writing my first paper, was that we didn't really know what the universe was made of. And because we didn't know what the universe was made of, we had to simulate all these models. First paper I had, we had 4 different models with very different contents of the universe. Some of them had lots of dark matter. Some of them actually did have dark energy, although we weren't sure that it existed. Some of them, in order to solve some of the problems, actually changed the kind of dark matter that we had and how much there was. So it was well established that dark matter made up about 70 to 90% of the mass. We now think it's closer to 85. But there was this strong theoretical prejudice based on this theory of inflation that I mentioned, that the universe should be flat. Okay? And in a matter-only universe, a flat universe must have the critical density. Okay, it must have that total amount of stuff that it would sort of go on expanding forever, always slowing down but never recollapsing. But when we looked at structure formation in those simulations and compared it to the data, it was much too clumpy. Okay, this was just one problem. There were also problems with the age of the universe, reconciling the ages of the oldest objects with the age we were inferring for the universe. So there were lots of problems. We really didn't know what was going on. And so we basically, a number of astronomers said, well, okay, let's try to go back and essentially do the same kind of experiment that Hubble did, right, measuring the expansion rate of the universe. People had actually been doing that this whole time, but there was an interesting breakthrough around this time, which was to find a new kind of standard candle. Okay, so this was the same kind of object that Hubble found, but Cepheid variable stars you can only see very close in, so you can't do that work out very far in the past of the universe. So you need something brighter, and one of the things that's quite a bit brighter than stars is exploding stars. Those are some of the most violent things that happen in the universe. They emit some of the most light of any objects in the universe, and there's a particular kind of supernova called supernova 1A, which are the explosions of massive stars. And so this was the kind of standard candle that was used for this experiment. So, and the problem with doing this, the reason people hadn't done it a lot earlier, is that supernovae are very rare. Okay, so there's only one per galaxy every 5,000 years. So if you just look at one galaxy, you're never going to do a very good measurement with this. So the breakthrough here was to scan large areas of sky very quickly and look for changes. Essentially, you look here, and you see it get brighter, and then you see it, and then you take the difference between these two pictures. And if you see something there, that means there was probably a supernova. So just in 1998, two different teams made this discovery, and they were able to essentially measure a Hubble diagram, in essence the same plot that Hubble made, except for now much, much further out in the history of the universe. And what they found was very surprising. So what they found was that the universe was not slowing down, right? Any stuff, any mass in the universe, any of the mass that we've been talking about makes the universe slow down. And that's not what they found. They found the universe's expansion was speeding up. They found that galaxies today are actually accelerating away from each other. Okay? So that's quite an odd state of affairs, and it means that there has to be something in the universe that's not matter. Okay? So this is basically the picture here. This is time going back, so they can measure these supernovae almost now over more than half of the age of the universe. So all the way back to what's called redshift 1.5 or so. Redshift 1 is about half the current age of the universe. So anything beyond that is further back in time. And so what you see is that basically, currently, the galaxies are traveling away from each other faster and faster. And that process kicked in at some time a little bit after the universe was half of its present age. So now to this picture that I showed you before, we have to add another option. Okay, so before I just showed you these three options, because these are the only three options that are possible in a universe made of matter. Okay, so now we've got to add this new option that instead of gravity making it slow down, some other thing has to be making the universe accelerate. Okay, and this was so exciting that Science magazine called it the breakthrough of the year in 1998. And the real puzzle here, I mean, so there's a measurement now that the universe is accelerating, but why? What could possibly be doing this thing? And the answer is we really don't know, but we've given it this name, dark energy. And I really like this picture, which I dug up. It says it's a plant nutrient additive, which, as far as I know, dark energy could be. And it says it stinks, but it rocks. So it does kind of stink. It's this extra element that's just kind of messing everything. This is so revolutionary that it shook the earth. Should I continue? All right. All right, now that I've had an appropriately dramatic moment here. I planned that, by the way. So the reason Einstein is pictured here in this Science magazine cover is that the amazing thing is that Einstein actually wrote down something like dark energy in his original equations of general relativity. And the reason that he did that was because when Einstein wrote down GR, no one knew that the universe was expanding. So he wrote down these equations, and because it was clear to him that matter had to make the universe expand or contract, essentially he had to put something else in there to make it stay fixed. Okay? And the expansion of the universe was discovered just a couple years later, and Einstein declared this writing down of this extra term his biggest mistake. And so it's now been called his second biggest mistake, was calling it his biggest mistake, because it turns out that he was right here. So although this story is really strange, it received some amazing confirmation just a couple years later, and I already showed you this picture. This is results from the WMAP satellite in 2003. And so this same picture that we think gave birth to the clumpiness in the universe is actually a very good tool for measuring the geometry. And remember, I told you this story about in a flat universe, the angles of a triangle add up to 180 degrees. So what you can do with this picture is essentially draw a really, really big triangle from yourself back all the way to the universe 400,000 years after the Big Bang and measure the angles. That's, in essence, what this does, and it measures the geometry in that way. And it's essentially measuring the size of these spots. Okay, that's the way you draw this triangle. And so the total amount of stuff in the universe is the amount of matter plus the amount of energy. So we learned before we discovered this dark energy that the mass wasn't enough at all to make the universe flat. It was only about 25% of what you need to make the universe flat. But the same stuff that provides this acceleration can make up the difference. Okay? So that's what we now think is going on. And we now have this very strange but actually quite consistent picture. Okay? So the constituents of the universe are basically quantified. We know how much of the universe is made of atoms. We know how much of the universe is made of matter that is not atoms, which we call dark matter. And we know how much of the universe is made of stuff that isn't matter. Okay? So when I say the matter density is low, it means it's much less than this magical critical density. The shape of the universe is flat. Again, it doesn't mean it's like a pancake. It just means geometry is like you learned from Euclid. This changes the age of the universe from what you would have with the same amount of matter because it changes the expansion rate. Remember that this expansion rate is directly connected to the age. And this new WMAP experiment actually provides a very precise constraint on what the age of the universe is. And we now think it's about 13.7 billion years. And that's really just plus or minus generously about 0.2. So it's really quite close to this. This is a very precise measurement. But again, we don't really understand what the rest of this 95% is. And I want to actually say that the 25% that's dark matter, although we don't know what particle it is and we haven't detected it, we know a lot about how it behaves. We know we have a pretty robust model called cold dark matter, which is really a fairly robust theory now. Makes lots of predictions on all kinds of scales. And we still, of course, need to detect this thing, but there is some hope for it, and there are good ideas for what it might be. The situation with dark energy is not like that. I don't think there are any great ideas about what it is. So what do we really know about it? We know that the universe is dominated by something that isn't matter. We know that this component is repulsive and not attractive. Right? Anything made of matter has to attract. This makes the universe expand faster and faster as time goes on. We know that this stuff seems to be fairly smoothly filling space. It's not very different in one place than it is in another. And it seems to have roughly constant energy per unit of space. Okay? And we don't really know whether it's constant either, but it's approximately constant. Okay? And that's about it. That's about all we know about this stuff. So you can go home now if you'd like. So, I mean, one of the amazing facts about this dark energy is if it is sort of a constant energy density of space, then as space expands, you have more space, and thus you have more energy in that space. So it's a very strange state of affairs, and you have that actually a very similar state of affairs in the very first moment of the universe in this process called inflation. And Alan Guth said about that process, the universe is the ultimate free lunch. Because of this, you basically get something for nothing. You get this energy just straight out of the expansion. So, okay, so let's just talk a little bit about what this stuff might be. So one possible explanation is that it's a cosmological constant. Okay, so that was Einstein's original idea, just this constant term, essentially, that he wrote down in the theory of general relativity. There's no particular idea about where that constant comes from or what it is really at all, except for that it could be, in principle, just some fundamental constant of nature with any value, in principle. But that's not very satisfying. The other possibility is that the vacuum has some energy. Okay, so this is sort of the most popular idea for what this stuff is. The energy, basically the vacuum itself, space, empty space, has some energy density, and then you have to figure out why it has that energy density and what it's doing. So I want to talk a little bit about that. It's not a crazy idea, actually, that the vacuum might have energy. For example, essentially, quantum field theory predicts this process I told you about, particles popping in and out of existence. That should actually create quite a bit of energy in empty space. Okay? And in principle, most likely, you might think that that energy would be repulsive. That thing would essentially so you might think that that energy is repulsive, and then it could be responsible for the acceleration of the universe. Okay? So let's do a little bit of a calculation about what we might expect in particle physics about how big those quantum fluctuations are. And if you ask the people who do these calculations, they tell you that the answer has this many zeros. I don't know, it's about a billion. I don't even know the name of that number. Anyways, it's a lot bigger than what's actually observed. So this is the number that's predicted. And the number that's observed is 0.7. So those numbers aren't very similar. And particle physicists have this funny thing that whenever they find a really, really large number, they like to cancel it with another really, really large number and say it's 0. So that's what most particle physicists assumed. This number was so big that it had to be essentially something that canceled out with some other thing. And so that was sort of the assumption until this measurement showed that it was 0.7. It's very hard getting a big number to cancel with another big number that's almost the same but a tiny bit different is actually quite hard and feels a little weird. So that's why it feels very unnatural. And there's another very unnatural thing here. There's this odd coincidence that, the number 25% is actually not that different from the number 70%, meaning the dark matter and the dark energy are roughly the same order of magnitude today. And that's odd only because if you look at what they must have been over the history of the universe, that state of affairs did not persist. Matter density is diluted when the universe expands. So the matter density was a lot higher in the past and will be a lot lower in the future as the universe continues to expand. Whereas this energy density of space, this dark energy, is a property of space itself, so it's essentially constant. So you get this funny thing that at early times, the matter was essentially everything. At late times in this universe, the dark energy is essentially everything, and we're in this kind of special time right now when they're roughly the same order of magnitude. And what's? The yellow part? Oh, that's ordinary matter. That's the baryonic matter, yeah. So that's the second puzzle. So although I think this energy density of the vacuum is probably still the best idea, although we don't understand why it has the value we have. We also don't understand it could be constant, could behave just like the cosmological constant, or it could be changing. Since we don't know what causes it, we don't know how it might have behaved in the past or in the future. Some people have proposed various modifications of gravity to explain away dark energy, and there are some plausible ideas here, much more plausible than the ideas to modify gravity to get rid of dark matter, which I don't think work. But there's lots of limits. You have to both be able to explain everything we know about the expansion history of the universe, as well as explaining, for example, tests of GR in the solar system and that kind of thing. So this is very, very hard to do. But maybe it's something totally different that we haven't even thought of yet. And I think the basic thing is that we really don't know. And in fact, some of the best minds in particle physics also agree with this. Steven Weinberg, who won a Nobel Prize for his work in particle physics, said right now, not only for cosmology, but for elementary particle theory, this is the bone in our throat. Another Nobel Prize winner, Frank Wilczek, maybe the most fundamentally mysterious thing in all of science. Ed Witten, who many people think is pretty much the smartest person alive, said it would be #1 on his list of things to figure out. So he hasn't figured it out yet. I might figure it out after the talk, but okay. So now that we've gotten this far, I want to do a little quiz about dark matter and dark energy. Do you think they're very similar or not? So can I have a show of hands for people that think, yeah, dark matter and dark energy, they're pretty similar? Okay, we got a few takers. Who thinks they're not similar at all? Okay, and who thinks they were similar only a long, long time ago? Excellent, we've got all answers. I'm very happy to see that. Okay, so let me give you a rundown. I probably would choose B, although there are some tiny elements of truth to A and C as well. So let me just give you a rundown of the differences here. Remember, dark matter is attractive, dark energy is repulsive. Dark matter is clumpy, right? It pulls stuff to it, makes the rich get richer and the poor get poorer. Dark energy is just smooth. It's very egalitarian. Dark matter is made of particles, we think, whereas dark energy is not made of stuff. It's a property of space itself. What do they have in common? Well, this is basically the main thing we have in common. If you try to take a picture of both of them, they look just the same. Just the same. So they have one other thing in common, which is that you actually, although you can't just take a picture of either one of them, you can actually get information about both of them by taking pictures of the universe, even in optical light, even with essentially a normal camera on a really big telescope. And that's one of the kinds of things that we're going to try to do in the next decade to sort this picture out. And the main thing that happens here is you can get information about these things not from the light they emit, but by measuring the expansion rate, as we already saw. That's where a lot of the information already comes from. And by measuring the growth of structure, this process of gravity bringing things closer and closer together. So there's lots of hard questions about dark energy. What is it and what caused it, I think, are pretty hard questions about dark energy that no one has very good ideas about. And these hard questions are really going to require both theoretical breakthroughs as well as experimental measurements. So that's why I think they're hard. There's some slightly easier questions which are essentially accessible with measurements of the universe. You can ask, is it constant everywhere? Or does it change over time and over space? So this is the question that we're going to try to answer in the next decade or two about dark energy. And hopefully, once we start with this question, that will inform these kinds of harder questions, and our particle physics colleagues will hopefully come up with some brilliant ideas. And it is a really interesting situation that we're in now, actually with both dark matter and dark energy, but dark energy in particular, which is that what is arguably the most important question in particle physics is actually not best answered at an accelerator. It's best answered by measurements of the universe. So that's actually, in some ways, a real interesting opportunity. It's an opportunity for particle physicists and astronomers to work together to try to answer these questions. And that's actually now happening, both here at SLAC and elsewhere in the world. And this is just a sampling of some of the projects that are planned over the next decade to try to learn more about the dark energy. So there's a couple surveys. These two on the right are both galaxy surveys. They're essentially surveys that attempt to measure lots and lots of galaxies quite far back in time and see how they're behaving. See if you can measure both of these things, the expansion rate of the universe and the growth of structure. This one, the Dark Energy Survey, is a project I'm involved with that is going to measure 300 million galaxies. Okay? And this project, the LSST DES, will probably start in about 2009. LSST is actually being led by people here at SLAC and Stanford and at Davis. But the camera for LSST will hopefully be built here. This is a very exciting project. It's a project that will take a picture of the sky, essentially a 15-second exposure of the sky, and measure the entire sky every 3 days. The entire sky that it can see every 3 days, and hopes to get information about 3 billion galaxies. So we think there's probably about 100 billion galaxies in our observable universe, but LSST is taking a big chunk out of that. These are two other projects. SPT is a project to measure clusters in the universe, basically the most massive objects. And this is not an optical telescope. It's a telescope that does something called the Sunyaev-Zeldovich effect, which I don't have time to get into, but it's essentially a way of detecting clusters far back in time. And SNAP is a proposed telescope, which also has some people here at SLAC involved in it. And SLAC's sort of targeting supernovae. But all of these projects will actually be able to measure supernovae and galaxies, as well as something called weak lensing, which is essentially something you measure from the galaxy distribution and is one of the best ways of mapping out where the stuff is in the universe. And so that's, again, the main goal of these projects, is to measure the expansion history of the universe. And there's lots of different ways to do that. Again, the two main ways are, what is the expansion rate? And there's this way that I already told you about, standard candles, which you can do with supernovae. And there's a similar kind of technique where instead of having something whose brightness you know, you take something whose size you know, and then you measure how that changes with time. And there's a technique called baryon acoustic oscillations, which is kind of a mouthful, but that provides a standard ruler. And then there's measurements of how the clumpiness grows. And this weak lensing thing is essentially a way to map out the matter distribution in the entire universe that you observe using the deflection of light. And it's called weak because you're looking for very, very small deflections that you can only do statistically with essentially millions of galaxies. So that's what we're going to try to do in the next decade, and I just want to spend a couple more minutes talking about the future. So it says, can I be honest for a second? We've got to talk about the future. So, okay, so what happens in the future of this universe? Well, let's just assume for a moment that it's a cosmological constant. This was a movie made by postdoc Michael Busha, who works here, taking the same kind of simulation that I showed you before, except for now, instead of just evolving it to the present day, which actually just happened, we're going to evolve it far, far into the future. This number A here is the scale factor. So when that was 1, that meant today. And when it's 10, it means the universe is 10 times bigger than it is today. And what you see is actually that stuff gets kind of boring. So there's again, in this picture, the expansion of the universe has been scaled out. So all of that expansion and acceleration, we're ignoring that. And you can see there's lots of stuff happening. In the early universe, still some stuff happening today, which we've now gone by. And then stuff really seems to slow down. And essentially what happens is that these fluctuations get frozen in. And the structures just stop. And because the universe is accelerating away, what that means in the end is that only the things essentially that are currently bound to us, or a little bit, or will be bound to us sort of in the fairly near future due to gravity, are going to stay bound to us, and everything else is going to get pushed away by this dark energy. So it's actually kind of a slow, painful, painless, actually, slow, painless death, which is just pretty cold and pretty boring. There are other more exciting ideas. Because we don't actually know what this is, it could do something totally different in the future. Who knows, right? Until we figure out if this thing is constant, we actually can't say. And I think very few people now think the universe will recollapse on itself because it's accelerating away from itself so rapidly now. That doesn't seem so plausible. But because we don't know what this thing is, it's still, in essence, a possibility. And there's another idea called the Big Rip, which is actually that instead of just accelerating, it accelerates so fast that space itself actually kind of just disintegrates. So I'll leave you with that kind of crazy idea and just summarize with this plot, right? We're in this state of affairs. We have dark energy is now very well established. We know these numbers. We know these numbers to better than 10% now, which is really a phenomenal thing that's just happened in the last decade. And so the universe's contents are extremely well quantified, but 95% of it is really not very well understood at all. And so we have this very strange stuff, makes up 70% of the universe, and its origin and nature are really pretty much unknown. And so the only thing I can say is really to stay tuned, and hopefully we'll figure some of this stuff out. And I will just leave you with the fox who said it best, which is the essential is invisible to the eyes. So thank you very much.
We'll take a few questions now, and then there's some refreshments courteously provided by Pierre Schwab upstairs. So in a few minutes, we'll retreat up there, and you can look for more people to ask questions of who are wearing baseball caps. So let's take a couple of questions for Risa now. I see one up here. You want to?
Yeah, so I'm not sure if I can repeat the question, but so let me just talk a little bit about matter and energy. This dark energy, so matter itself does have energy, but the energy that matter has is actually, in some ways, fundamentally different than the matter that space has. They do actually behave differently in GR. This sort of energy density of space is fundamentally different than the energy that mass has. There are some theories in which dark energy and dark matter are more related in detail and can turn into each other. I don't know whether those theories are reasonable or not, but people do try to come up with them. I'm not sure what the question is about time, but you can ask it again afterwards. Yeah.
You have a pie chart, I think it was number 9, but essentially you have a pie chart with the percentages. Do you know more or less
I used to know the number in ergs, but I've forgotten it. We do know how much it is, though. I mean, we do actually know. I don't know what it is in any units, I can tell you. But we do actually know the amount. It's not just the percentages that we know. It's very well quantified what the amount is. And that's related to what I was talking about the universe being almost exactly flat. That tells you sort of what the total number is. But it actually does correspond to a specific amount of energy per unit space. But that's in units of the critical density. Okay, so that's in units of the amount that it takes to make the universe flat. To make the universe... It's normalized to that number. Yeah. So, I don't know that there's any evidence for dark energy in our own galaxy. We really only have evidence for dark energy on very, very large scales. But we do have evidence for dark matter in our own galaxy, and that essentially comes from looking at the motions of stars in our galaxy, from looking at how we have measurements of dark matter essentially in many, many galaxies. There's another piece of evidence for dark matter in our galaxy which is actually quite new and interesting, which is looking at the disruption of galaxies that come in to the Milky Way. Things like you might have heard of the Large Magellanic Cloud or the Sagittarius Dwarf. The Milky Way has about 5 years ago, it had about 10 of these satellite dwarfs, and now it actually has about 20. Many have been actually discovered in the last couple of years, which is very exciting. But one of the things that we've now seen is we can actually see those things getting disrupted as they come into the Milky Way. And that disruption process depends on the amount of stuff there is, and that really implies that we do have dark matter in our own Milky Way. We basically think there's dark matter surrounding every galaxy. In the back? Yeah.
Oh, hi. Yes. You said that dark energy has roughly constant energy per unit space, and I was just curious, was that an assumption or some kind of conclusion? From the last thing you said, I'm guessing it probably was an assumption that a conclusion based on evidence. What or whose work led to that conclusion? And it's actually a two-part question. That's part A is what or whose work led to that conclusion or assumption, and part B is were the measurements that were taken to determine this from the earliest stages of the universe, or perhaps more recently, like in the past couple billion years? And actually, part C, if the dark matter, as you mentioned, were to ever evolve in the future, would that not then affect the expansion rate of the universe with respect to its critical density? Or what are your thoughts on that?
Let me answer the first part first. So we think that there is evidence that shows that it's approximately constant. There is no evidence that shows it's exactly constant, either over space or over time, and that's one of the main things that we're trying to figure out. We know it can't be very, very rapidly changing. And the evidence for that is actually, it's not in the earliest stages of the universe. It's mostly over the second half of the universe, and it comes from, again, the observations of supernovae and of the evolution of galaxy clustering and of the evolution of the clumps in the universe. There's the number of people whose work led to that conclusion is so numerous that I won't even attempt to name them. And you can ask the second part. I've already forgotten, so you can ask it later. I'll move on to someone else. You in the back. Yeah, you. No. So the interesting thing about dark matter, we actually think dark matter is here, flying through you and me as we speak. It's kind of exciting. I can't feel it. I don't know. Maybe you can, or maybe it's easier to feel on Halloween or during earthquakes. But dark matter particles, at least our best theories about dark matter particles is that there's lots of them here, but because they don't interact, they basically can travel through your body and through the ceiling of this auditorium and go right through you. There is actually a possibility to detect them on Earth because although they barely interact, they interact ever so slightly. And so what people try to do is they build experiments underground so that they're shielded from lots of other particles and try to look for very, very rare occurrences of dark matter interacting with things. Yeah.
You were saying things as far as physical changes, like how the galaxies are expanding and getting larger, and everything inside the galaxy would be getting larger also, like planets and things like that?
No, no. So you and I are not getting larger. At least depending on what we eat. And there's a famous quote from a Woody Allen movie where his mother says to Woody Allen as a kid, because Woody Allen is very concerned that Brooklyn is expanding, and his mother says, "Brooklyn is not expanding." And that's right. Brooklyn is probably not expanding. San Francisco is almost certainly not expanding. So essentially anything that's gravitationally bound is not expanding. So the Milky Way also is actually not expanding away. One side of the Milky Way is not expanding away from the other side of the Milky Way. They are bound already from gravity, and they've sort of decoupled from the expansion of the rest of the universe. So things are just getting farther apart. They're not getting bigger. That's right. Yeah. The mechanism for gravity. I don't think I even understand that question. So, not that it's a bad one, but I just don't even know what it means. No, I don't think we have learned anything about what causes the force. I mean, in the standard model, there's a particle called the graviton, which mediates the gravitational force. But other than that understanding, I don't think it's a lot deeper than that. Yeah.
You said that energy density increases as the universe expands. Now, in high school, we all learned the principle of the conservation of energy, and some of us flunked the test because we didn't get it. Does that mean that, it's all wrong?
So that's actually a difficult question. The energy is conserved in the normal ways you thought of it in high school physics. That is still true. But it is true that, in essence, if there is a constant energy density of space, then as space increases, you do get more energy. And that is something different than conservation of energy. Yeah. Yeah. Sorry.
Normally, we perceive baryonic matter basically through photons.
Mm-hmm.
So could this mysterious stuff of dark energy and dark matter be perceived through some other boson, like maybe this mystery graviton?
Yeah, so very possibly. I don't know that there are any ideas about how that works for dark energy. For dark matter, there are lots of good ideas for how that might work. So if dark matter is mostly made of some particle, some of the most popular theories for what that particle is some sort of so-called supersymmetric particle. And that's the idea that every particle that we know that currently exists has some partner that we haven't detected yet. And there is actually some hope of detecting that in accelerators, especially once the thing called the Large Hadron Collider turns on. So if it's a particle, there are forces that mediate it, and it probably actually does interact very slightly with normal particles. And that's why we think we have some hope of detecting dark matter, either directly or through its interactions with photons. There's other experiments that are going to happen, one called the GLAST satellite, which was actually built here at SLAC, which is going to be launched looking for very high energy gamma rays. And that's the hope there is that you can detect actually photons that were created in these interactions.
So I'd like to suggest that at this time we break, thank Risa again, and then we can ask more questions privately. So thanks again, Risa, for a great talk.